In this lesson, we're going to look at finding limits algebraically, meaning using equations. And we are going to reference graphs from time to time, but mostly we're going to just work with equations. So the first method that we use, which is kind of our go-to method, is direct substitution. This just means plug in your x value and see what comes out. So we have the limit of x squared plus 2x minus 4 as x goes to negative 1. So plug in a negative 1. We've got negative 1 squared plus 2 times negative 1 minus 4 gives us 1 minus 2 minus 4 equals negative 5. So if we take a look at the graph, what does this actually look like? Why do we get a negative 5? We pull up the graph and we see that as x goes to negative 1, that would be coming in from the right side, coming in from the left side, we end up with this point at negative 1, negative 5. So here's your graph, parabola, we go towards negative 1, y value of negative 5. Remember, that's what this means in terms of the graph. Then we take a look at the next one, which is just limit of 6 as x goes to 2. Remember that this 6 is my y value, so this is basically the equation or the line y equals 6. So if I was going to look at the graph of that, it's just a straight line right across the middle of my graph at a y value of 6. So what value do we approach? Well, no matter what value we approach, we always hit a y value of 6 anywhere along the line. So this is kind of a weird one, but a no-brainer in terms of doesn't matter what we approach the value of 2, we're going to have our limit equal to 6. So again, direct substitution, first method we're going to try, and we try that with these next ones. We want to plug in x equals 0. We got 4 times 0 minus 5 times 0 over 0 is going to be 0 over 0. And this is what we call the indeterminate form, which means we can't figure out what the limit is yet. We've got to do some extra manipulation. So in this case, the hint here is factor and cancel. So we're going to see if we can factor this. We got common factor of x, 4x minus 5 over x, and happy day, our x's will cancel. So now what we're going to try is take the limit of x goes to 0 of just what was left behind, 4x minus 5, and we're going to try direct substitution once again, plug in a 0, so we got 4 times 0 minus 5 gives me the limit of negative 5. How does this work? Let's take a look at the graph again. So this time, our graph basically looks like a straight line. So we want to figure out the limit as x goes to 0 is coming in from the right side to negative 5, coming in from the left side to negative 5. I can even trace along here. I can see my y value getting closer and closer and closer to negative 5. But if I actually get there, it tells me 0 undefined. That's because there's a hole in the graph right here where I canceled stuff out. But the limit still exists around here. That's why we could cancel to find, but there's a hole at x equals 0. Limit negative 5, but a hole at x equals 0. The next one, if we plug in x going to negative 7 into this, what you're going to find is again that we get 0 over 0, or the indeterminate form. If you don't believe me, go ahead and try it, which means again we need to figure out how to factor and cancel if we can, which is going to be our go-to method when we've got this 0 over 0. So because we've got a 0 on the top, I'm almost guaranteed that one of my factors on the top is going to be an x plus 7, so it will cancel out the x plus 7 on the bottom. So I can kind of use that to help me figure out what my other factor should be. So I need my first two factors, my first two terms to multiply to 2x squared, so I think this should be a 2x. And my last terms should multiply to negative 7, so this should be a minus 1. Double check that you do get your middle term. I have x, so that's minus x plus 14x is a plus 13x is going to work. And then I can cancel the x plus 7s, which makes me happy, and now I have the limit as x goes to negative 7 of just 2x minus 1. And again, once I've done that cancel, I can plug in my value of negative 7, use direct substitution. This gets me, whoops, not divide, equals negative 14 minus 1 is negative 15. So again, let's just take a look at the graph, make sure that makes sense. So again, we got a straight line graph, and we're thinking limit as x goes to negative 7. So here's negative 7. I can see that my y value is going to be negative 15. And as I expect, there is a hole at negative 7 where I canceled out that factor. So there's my negative 7. But as I go from both sides, I do get close to negative 15 right there. All right, so that's direct substitution, factor, and cancel. Now we're going to take a look at an example where the limit actually does not exist. We've seen some of these graphically where we've got either a jump discontinuity and our limits from both sides are different, or we're going with an asymptote and going to infinity. So again, I don't know what type I'm going to get before I start, so I'm going to try direct substitution, and I plug in -6 squared plus 4 times -6 plus 3 over -6 plus 6. Well, on the bottom, it's easy to see that I'm going to end up with 0. But on the top, I've got 36 minus 24 plus 3, and that is not going to be 0. So this is actually not an indeterminate form. I don't have 0 over 0. What I have is a limit that does not exist. And if I was going to try the factor and cancel thing, I would try factor the top, and I'd get x plus 3 and x plus 1 is going to give me top over x plus 6. Nothing cancels. And I can also see, looking at this, that I'm not going to get a 0 from either of these factors when I plug in the -6. So what I've got here in this case is limit does not exist. Again, let's just take a look at the graph to see why the limit doesn't exist. So you don't have to have this graph memorized. You just need to be aware that at this value of -6, which would be right about here, I've got this asymptote going up and going down. So whenever I get a number over 0, what I'm looking at is an asymptote, and the limit does not exist. All right, couple special limits with trigonometric functions, and these ones you're at this point just going to need to memorize. We could look at the graph and see kind of what's happening, but it's going to be actually just quicker to say this is what they are, memorize it, know it. It's going to save you time as we go along. So limit as x goes to 0 of sine x over x, or could also be x over sine x, both are going to be the same, are both equal to 1. Equal to 1. And the limit as x goes to 0 of 1 minus cos x over x, notice there's an extra 1 minus here, or -1, is going to be equal to 0. This is equal to 0. So again, you're going to just need to memorize it. The key is that they all are x going to 0, x approaching 0 for every single one of them. And for the sine ones, the ones involving sine, they are equal to 1. And maybe one way that you could kind of remember that is because the I in the middle of sine kind of looks like a 1. So again, we're dealing with sine x over x, we're dealing with 1. On the other hand, the ones with cosine, 1 minus cos x or cos x minus 1, both over x, are going to be 0. Think about the O in the middle as being like a big fat 0. Now, it's not just cos x over x, that's something different. 1 minus cos x over x, or cos x minus 1 over x, is equal to 0. And one of the reasons that you do need to memorize these is because if we try direct substitution, every single time we get 0 over 0. If you don't believe me, go ahead and try it on your calculator. But sine of 0 is 0, so we'd have 0 over 0, and cosine of 0 is 1, so 1 minus 1 over 0 is also going to be indeterminate. So we can use these to solve expressions that are a little more complicated than what you see here. So if I take a look at number 6 down there, I'm dealing with a sine. But in this case, I'm not dealing with sine x over x, I have sine 3x over x. So in order for me to use this idea, use this identity, use this that I've memorized, I actually need this 3x to match the bottom. I can't change the 3 inside the sine function. I can't do anything. It's kind of stuck inside, but I can turn this into a 3x on the bottom. And I can't just add an extra 3 on the bottom unless I also add the extra 3 on the top. So these 3's would cancel out if I wanted them to, so I'd be back to what I started with. But I don't want them to cancel out because I want this 3x and this 3x to match, so that this part of my expression is equal to 1 from this rule here, limit x goes to 0 of sine x over x equals 1. So this part equals to 1. And again, double check, but x goes to 0 is the condition that we need every single time. So then this is essentially, this 3 is going to multiply this 1. So this is going to be 3 times 1 equals 3. And that's kind of a handy thing, actually, we can use as a shortcut in future questions. because this 3x is actually going to give us the answer right away. The fact that there's a 3 inside my sign is going to give me the answer every single time. For example, if I had the limit as x goes to 0, remember always has to be 0, of sine 14x over x, this is going to equal 14. And you could do this manipulation to show why. You can multiply by 14 over 14. And then this part here is going to equal 1. And then I have 14 times 1 gives me 14. Or you can just go, oh yeah, I remember how this works. Make sure you do remember why it works, how it works, so you don't apply it when it doesn't apply. But if you have a 14 on the top, it actually works out pretty well that you've got it equal to 14. And vice versa, actually. If I have something like the limit of x going to 0 of sine x over 5x, for example, what happens there, if I want to figure out what this is, again, I need this 5 to go away, and I can factor it out the front of my limit. So I got limit x goes to 0 of 1/5 sine x over x. And this is just going to be, well, the sine x over x, this part is equal to 1. And then I just have 1/5 times 1 is 1/5. So in other words, whatever number I have on the bottom ends up being on the bottom of my fraction, and if whatever number I have on the top ends up being on the top of my fraction, if I have a fraction, or it's just 3 over 1 in this case. So that kind of, you've seen why it works, you've seen the manipulation, but that's kind of a neat little shortcut just to skip right to the answer if you remember why it works, how it works. And that's actually going to be true in this case as well, whether I have sine 7x over sine 9x, even though there's no x's involved, and I'm going to show you why that works. What I can do is I can actually break these into 2 fractions instead of just 1, so I'd have sine of 7x over 1 times sine of 9x needs to go on the bottom, 1 over sine of 9x, and then in that case, I can multiply top and bottom, or in this case, bottom of this fraction and top of this fraction by x, so they would cancel out and get me back to where I started. So I haven't actually changed my question. I've got sine of 7x over x and x over sine 9x. And I know from my shortcut that this is going to give me 7 over 1 if you like, and this is going to give me 1 over 9, because I have a 9 on the bottom, which is going to equal 7 over 9. So pretty handy trick. Again, see how it works, think about why it works, but this is a handy trick to be able to skip right from the 7 over 9 that I saw at the beginning to the end. All right, let's take a look at an example with cosine. Now, you might be thinking, okay, what happens if this doesn't look exactly like what I got up here, so try direct substitution, plug in x equals 0. I've got 1 squared minus 1, well, that's 0, and I've got 0 times 1 plus 1, well, that's still going to be 0. So I do have the indeterminate form, which means I need to do something about this. And the thing I need to do is factor and cancel, because I don't have either of these expressions directly. So maybe if you've been thinking hard, you can see at the top how I'm going to factor this as a difference of squares. So this ends up being limit x goes to 0 of, this is going to be cos x plus 1, cos x minus 1. Can you see that difference of squares? And then over x, cos x plus 1, which means that my cos x plus 1 can cancel my cos x plus 1, and then what I've got is the limit of x going to 0 of cos x minus 1 over x, which is the second form of my cos limit. So this is going to just equal to 0. Even though, again, if I tried direct substitution, it would be 0 over 0. If I look at the graph, which we could if you wanted to, I would see that limit x goes to 0 of this graph actually does go to 0. All right, so that's it for this lesson. And now's your chance to practice, and good luck on your mastery check.